In this lesson, we're going to look at how we can solve exponential equations. So there's three different methods that we're going to use depending on the equation that we start with. So method one is making the bases the same. So if it's possible, we want to try to make the bases the same. Sometimes this might involve rewriting both bases. Once the bases are the same, we cancel the bases and set the exponents equal to each other. And then we solve for the variable. So if we look at this example here, 8 to the x is equal to 4. So first we want to see, can we make the bases the same? So when we're doing that, we want to look for the smallest base, which we have as a 4 here, and see if we can make the other base, 8, have the same base as the 4. So if I try to make it 4 to the first, right, that's just 4. 4 to the second is 16. So I can't raise 4 to a power to get 8. That's a whole number. So we want to think, can we change both bases? Now both 8 and 4 we can rewrite as having a base of 2. So instead of 8, we can write this as 2 to the third. And the x that's in the exponent is going to stay up in the exponent with the 3. And then 4 is going to be 2 to the second. So we have the same base now. And once the bases are the same, we're just going to take those exponents and set them equal to each other. So 3x is equal to 2, and then that means that x is equal to 2/3. And unlike solving logs, we don't have to check for an extraneous solution. These won't have them, so we just solve for x. So let's look at a few more examples of this. All right, so 3 to the x minus 1 is equal to 81. So 3 is my smallest base. Can I make 81 have a base of 3? Yes, I can. So I'm going to keep 3 to the x minus 1. 81 is 3 to the fourth. Now that the bases are the same, I'm going to take those exponents and set them equal. And then I'm going to solve for x. So x equals 5. All right, number 2, 5 to the x minus 4 equals 125 to the 2x. Again, our smallest base is 5. So can we make 125 have a base of 5? Yes, we can. So 5 to the x minus 4 is equal to 125 is 5 cubed. And the 2x is in the exponent still, so that's going to stay up in the exponent with the 3. Now that the bases are the same, we're going to take those exponents and set them equal to each other. So now we have x minus 4 is equal to 6x. And then we're going to solve for x. So 5x is equal to negative 4. X is equal to negative 4 over 5. Okay, and then in number 3, we have 8 and 1 as our bases. So 1 is the smallest base. So can I make 8 have a base of 1? Well, 1 to any power is going to be 1. So I can't do that. But remember the property that anything to the 0 power is 1. So what I can do here is keep the left-hand side as having a base of 8. And I can rewrite 1 as a base of 8 to the 0 power. Now the bases are the same. So 3x plus 1 equals 0. 3x equals negative 1. X is equal to negative 1/3. So these are all examples where we can make the base the same. So here's a second scenario. Even if you can make the bases the same, you can use the next two methods that we're going to use. But making the bases the same is the easiest method. So if you can do that, you want to do that. Here's method 2. You have an exponent and a variable on one side. So you want to isolate the base and the exponent, and then you want to add, subtract, multiply, or divide as necessary to get the base to the exponent alone on one side. Once you have the base to the exponent by itself, you're then going to convert to logarithmic form. And then we'll isolate and solve for the variable. And sort of similar to how we did logs or the ln's last time, there's two answers you're going to get, the exact and the approximate. The exact answer will have a log in it. The approximate answer is going to be what we get after we plug it into the calculator. And we want to make sure we're plugging it in correctly. And I'll show you kind of how to do that in a little bit. And then we want to make sure that we round to at least 2 decimal places. You can have more, but not less. So let's look at this example. So 3 to the 2x is equal to 100. So the first thing I want to check is the base to the exponent isolated? So I already have 3 to the 2x by itself. There's nothing else over there. Um, I then would sort of ask myself, can I make the bases the same? So looking at 3 and 100, I can't make 100 have a base of 3, and I can't change both bases because 3, nothing to raise to a power is going to give me 3. So I can't use that first method. So what we're going to do is convert this to logarithmic form. So remember, to convert it to logarithmic form, we have log, and then we're going to use this counterclockwise motion. So the base of the exponent is a 3, so the base of the log is a 3. 100 equals 2x. So we want to get x by itself, so we divide by 2. So our exact answer that we get would be x is equal to log base 3 of 100 over 2. This is exact because it has log in the answer. And if I want to find my approximate answer, I'm going to plug this into the calculator. So using the calculator, if you're using one of these classroom set calculators, there's a button that changes the base on the log. So right now, if I hit this log button here, that has a base of 10, and we can use that, and I'll show you that in a minute as well. But we can use this math button right here. If you scroll down to log base, which is right here, hit enter, we can put the base in on the log. So it was log base 3 of 100. And now we want to divide it by 2. We want to make sure that we take that cursor and we bring it outside the parenthesis. So that way we're dividing the entire number, which is log base 3 of 100, by 2. If you keep it inside, you're just dividing the 100 by 2, which is going to be log base 3 of 50, which is not the same thing at all. So we go ahead and hit enter. And this is going to give us about 2.096. So I'll go over here, 2.096. And this is my approximate answer. Now, if you don't have a calculator that does have this log base, remember that we can use the change of base formula. So if I want to do log base 3 of 100 and I don't have that function on my calculator, I can do the regular log button, log of 100 divided by log of the base, so log of 3. This is going to give me the numerator part, and now I'm going to divide this by 2. So I get the same answer of 2.096. It's just a matter of, do you have the function that changes the base for you, or do you have to do it in 2 steps? Okay, let's look at a couple more. So here in number 1, we don't have the base to the exponent isolated. So what we need to do is isolate that. So first thing I'm going to do is subtract 4 from both sides. So you want to do any addition or subtraction first. So now we have 3 times 5 to the 3x minus 1 equals 21. We still want to get that base to the exponent by itself, so we're going to divide both sides by 3. So these will cancel. So we get 5 to the 3x minus 1 equals 7. At this point, you want to ask yourself, can we make the bases the same? 5 and 7, unfortunately, we cannot make the bases the same. So we're going to change forms. So this is going to be log base 5 of 7 is equal to 3x minus 1. So to get the x by itself, we're going to add 1 to both sides. Now be careful here. When we add 1, we're not actually adding 1 to the 7. So this does not become log base 5 of 8. It's log base 5 of 7, which is a number, and then we're going to add 1 to that number. And now we want to get x alone, so we divide by 3. So our exact answer would be log base 5 of 7 plus 1 over 3. And that's our exact. And then for our approximate, we're going to plug it in the calculator. Clear that here. So I'm going to use that log base button. I'm going to show you 2 ways you can do this. So log base, and it was log base 5 of 7 And again, make sure you're outside the parenthesis before you add the 1. Now, if I try to divide by 3 here, the calculator will only divide the 1 by 3, not the entire log base 5 of 7 plus 1. So the calculator is only as smart as the person that's using it. So we can do one of two things here. So I'm going to do, since I already, have it set up like this. I'm just going to figure out the numerator. So log base 5 of 7 plus 1 is this number. And then I'm going to divide it by 3. So this is actually my answer. If you want to put everything in at once, you just have to be careful and you need to use parentheses. So I'm going to put parentheses, and then I'm going to do the numerator, which was log base 5 of 7. Go out of the parentheses, plus 1. I'm going to close the parentheses. So this is the whole numerator, and then I'm going to divide it by 3. So this is one step, and I get the same answer. Or you can do the numerator first, and then take that answer and divide it by 3. So either way, we get 0.736, and that's our approximate. So 0.736. Okay, and then in number 2 over here, we notice that we do have an e here. So the base to the exponent's already isolated, so that's good. If I go to change forms, I'm just going to put this up here first because we're not going to actually use this. The base is e, so log base e of 0.12 equals x minus 9. But we don't write log base e. Log base e is the same thing as the natural log. So what I'm going to do here is just say ln of 0.12 is equal to x minus 9. And to get the x alone, I'm going to add 9. And just like before, be careful because we're not actually adding the 9 to the 0.12. It's ln of 0.12 as a number and then plus 9. So this is our exact. And for our approximate, if we plug this into the calculator, the ln button is right here next to the 4. It's to the left of the 4. So I'll have ln of 0.12. I need to close the parenthesis and then add the 9. So if you add the 9 before you close the parenthesis, it's going to be the ln of 9.12, which is not the same thing. So we get about 6.88 as our approximate answer. Okay, so now we're going to use this method in order to solve some applications. So a few lessons ago, we looked at the applications and we learned that there was 4 different equations that we could use. We have the exponential growth, exponential decay, compound interest, and compound continuously. So when we did those before, we were most likely solving for the final amount. So after 10 years, how much money was in the account. That's what we were doing. There was one problem that we looked at where we needed to use the table on the calculator to estimate the time. So sometimes it would say, how long does it take for the account to reach an amount of $500? So when we did this before, we had to use the table of values in the calculator and kind of estimate. Also, on your radical functions project, we had to find how long it took for the price of a house to double. And at that point, I said just use guess and check, plug numbers in. Now that we know how to solve for variables that are in the exponent, we can actually solve for the exact time. So let's look at this first question. So here we see you buy a computer for $2,100. The computer's value decreases 20% per year. How many years until the computer is worth less than $500? So since it says the word decreases, this is an exponential decay function. So if you remember the equation, a of t equals a times 1 minus r to the t. It's a decay, so we're subtracting the rate. So let's identify all this information. So a of t is our final amount, and they tell us $500. Right? We want the computer to be worth less than 500, so 500 is like our ending amount. Little a, is our starting amount or our initial amount, which is how much we bought the computer for, which is 2,100. Our rate is 20%, but we have to change it to a decimal, so 0.20. And t is our question mark. T is what we're trying to solve for. So let's plug this in. So a of t is 500. A is 2100, 1 minus 0.20 to the t. So if I clean this up a little bit, 2100 times 0.80 to the t, we want to get the base to the exponent by itself like we were just doing in the previous problems. So we have to get rid of the 2100. So we're going to divide both sides by 2100. So we can get a decimal version for this if we want to. I'm just going to cancel out the zeros and make this 5 over 21. And that's equal to 0.80 to the t. Now, if you like the exponent to be on the left, you can switch this entire thing and say 0.80 to the t is equal to 5 over 21. Either way is fine. So now that we have that base to the exponent by itself, we're going to change this to logarithmic form. So we have log base 0.80 of 5 over 21, and that's equal to t. So since this is a word problem, this doesn't really make sense as a number because we don't know what that is. So we're just going to use the calculator. So we're going to do math, and we'll go to log base. The base is 0.80, and then 5 over 21. And then we hit enter. So it's going to take about 6.43 years. So we'll say t is approximately 6.43. And since this is a word problem, we want to make sure we do have it labeled with the proper units. So we say this many years. And you can leave this as a decimal. If you want to round it, always round up. So if it's anything after 6, it's in the 7th year. So you can say in the 7th year, or just write it precisely like this. Okay, let's look at number 2. Suppose you deposit $2,500 in a savings account that pays you 5% interest per year. How many years will it take for you to reach $8,000? So you're getting money. So this is a growth function. So A of t equals A times 1 plus R to the t. So again, let's identify our information. A of t is our final amount, which is 8,000. Little a is our initial amount, which is 2,500. R is our rate, which is 5%, so 0.05. And t is going to be our time, which we don't know, which is what we're solving for. So let's plug it in. 8,000 equals 2,500 times 1 plus 0.05 to the t. I'm going to clean this up a little bit by combining the 1 plus 0.05 to make it 1.05 to the t. I want to get the base to the exponent by itself, so I'm going to divide by 2,500. So I'm going to make this, I'm just going to write this as 80 over 25 for now. Again, just canceling out the zeros to make it a little bit easier. So these are gone here, and that's equal to 1.05 to the t. So again, I'm going to change forms. So this is going to be log base 1.05 to the 80 over 25 is equal to t. And then I'm going to just plug this right into the calculator to find my approximate amount. Again, go to log base, and I'm going to put in 1.05 as, 1.05 as my base. And then I'm using 80 over 25. Okay, and I get about 23.84 years. So 23.84. It's a word problem, so don't forget our units, which is years. All right, so let's look at this last word problem here. If $3,000 is invested at 6% compounded continuously, then how long will it take for the investment to grow to $10,000? So again, we're looking for keywords, compound continuously. This means that we're going to use the compound continuously formula, which is A equals PE to the RT, that PERT equation. A is our final amount, which in this case is 10,000. P is our principal, which is our initial amount, which is 3,000. E is E, that's the button in the calculator. R is our rate, so 0.06 since it's 6%. And T is what we're solving for. So we have 10,000 equals 3,000 E to the 0.06 T. Just like before, we want to isolate the base to the exponent, so we're going to divide both sides by 3,000. And again, I'm just going to chop off the zeros. So I end up with 10 over 3 equals e to the 0.06t. Now that the base to the exponent is isolated, I'm going to go ahead and change this to logarithmic form. Because I have an e, I'm using ln. So this will be ln of 10 over 3 equals 0.06t. To get t by itself, we're going to divide by 0.06. And then we get, our exact answer of ln of 10 thirds over 0.06. But again, that doesn't really make sense because we don't know what that is. So plug it in the calculator. So we're going to do ln, since we're using e. It's ln of 10 over 3. Close the parenthesis. And then we're going to divide it by 0.0. Oh my gosh, oops. 0.06, if this will let me use this properly, 0.06. So it'll take about 20.07 years. So t is approximately 20.07 years to reach that amount. Okay, and then the last method that we use is what happens when we have an exponent and a variable on both sides. So I'm just going to come back and kind of refer to this as I go so we can see what we're doing here. So first thing I want to do is see if I can make the bases the same. I see 3, I see 8. Unfortunately, I can't make the bases the same. So step 1 says to take the log of both sides. So in math, whenever we do something to one side, we have to do the same thing to the other side to keep it balanced. So if I want to multiply by 2 on one side, I have to multiply by 2 on the other side. So if I take the log, that just means I'm going to write the word log on both sides. So log of 3 to the 4x is equal to log of 8 to the 2x plus 1. So take the log of both sides, check. Step 2, move any exponents in front of the log. So once I write the word log, these are now logs. So all of the properties of logs hold true, which means that any number that is an exponent can be brought to the front. So this is going to become 4x log 3, and then that's going to be 2x plus 1 log 8. Okay, so all we did here was move those to the front. Okay, so step 2 is done. If there are multiple terms in the exponent, distribute them to the accompanying log. Okay, so what that means is more than one term means that there's something separated by addition and or subtraction. So when I look at the exponent of 4x, that's one term. They're together through multiplication, so that's one term. But 2x plus 1 is two terms because there's a plus sign separating them. So what we're going to do is take the 2x and the 1 and distribute it to the log 8. So what's going to happen is the 4x log 3 stays the same on the left. This is going to become 2x log 8 plus 1 log 8. Okay, so I'm distributing what was in front. Step 4, move all log terms that have an x to the same side and all terms without an x on the other side. So looking here, this log term has an x, this log term does not. So what we're going to do is take this 2x log 8 and we're going to subtract it to the other side. So we have 4x log 3, and that's equal, 4x log 3 minus 2x log 8, and that's equal to log 8. Okay, so we took this term of 2x log 8 and we subtracted it to the other side so that the x's can be together. Then we want to factor out the x. So our goal here is to get x equals. We want to solve for x. So we need to take out the x. Now, even though both of these have like a 2x in common, we don't want to pull out a GCF. We only want to pull out just the x. So I'm going to go ahead and factor out just the x. So this is 4 log 3 minus 2 log 8. And that's equal to log 8. Okay, so I just pulled the x out of these two. And then it says to solve for the variable. Okay, so all we're going to do is solve for x. So I'm going to go ahead and if I want to get x alone, actually I'll go back to here real quick. If I want to get x alone, I have to divide both sides by this. So I'm dividing by 4 log 3 minus 2 log 8 on both sides. 4 log 3 minus 2 log 8. So this cancels out. And we end up with x equals log of 8 over 4 log 3 minus 2 log 8. Now technically, this is solved for, right? Exact answers have logs in them, so we have that. But it says you can condense the logs by using the properties of logs. So I'm going to go ahead and do that. So the denominator has more than one log, so I'm going to condense that. So the top will stay log 8. The numbers in front are my exponents. So I'm going to make this log 3 to the 4th minus log 8 squared. I'm just going to keep going underneath here. So I have log 8. Because I have subtraction, that means I really have division. So I'm going to make this log of, so 3 to the 4th is 81. 8 squared is 64. So if the numbers are easy enough to raise to the power, do that. If they're not, you can just leave them as 3 to the 4th and 8 squared. So this would be my exact answer that's fully condensed. It's the same thing as if we looked at the first blue that I wrote. So if I plug this into the calculator, it's easier to plug it in when it's condensed. So I'm going to go ahead and show you both ways. So if I plug in the condensed version, I have log 8. Notice I'm using the log button because the base is a 10 since it's a normal log. And now I'm going to divide by log of 81 over 64. So that's condensed. So I get an answer of 8.827. Now if I wanted to plug in this one, we just want to be careful because of the use of parentheses. So we have log of 8, close your parenthesis, divided by. You have to have an open parenthesis first if you're going to be doing it not condensed. So we have an open parenthesis, 4 log 3, close that parenthesis, minus 2 log 8, close that parenthesis again. So every parenthesis should have a matching one that closes it. So this gives us the same answer. I would recommend condensing it because if you forget to put a parenthesis in here, you're going to get the wrong approximate answer. So we said that our approximate answer would be about 8.827. Okay, so we're going to look at this last problem. So again, see if you can make the bases the same. 5 and 2, you can't, unfortunately. So we're going to take the log of both sides. So log of 5 to the x minus 1 equals log of 2 to the x. Any exponents are going to come down as numbers in front. So we're going to have x minus 1 log 5 equals x log 2. Because the x minus 1 is 2 terms, we're going to distribute that. So we're going to have x log 5 minus log 5 equals x log 2. Now we want to get all of the x terms on the same side. So it doesn't matter if we move this term over here or this over here and then the negative log of 5 to the other side. Whatever makes sense, do. So I'm going to move this x log 5 to the other side. So I have, let me change colors. So I'm going to keep this negative log 5 on this side. And on this side, I have the x log 2. And then I'm going to move this x log of 5. So subtract x log 5. So I have, oops, negative log 5. So now I'm going to factor out the x. So x is going to get factored out. I have log 2 minus log 5. I want to get x alone, so I'm going to divide both sides by log 2 minus log 5. So this cancels out. So what I have now, I'm just going to write it as x equals this way. X equals negative log of 5 over log 2 minus log 5. Now, technically, again, this is correct. I can leave it like this. You do not want to cancel the log 5s, right? This log 5 is attached to this one through subtraction, so we can't just cancel out part of something. So what I am going to do is try to condense it. So I have negative log of 5 on the top. Because I have subtraction, this is really going to be division. So I have log of 2 over 5. So this would be my exact answer. And then I'm going to do negative log of 5 divided by log of 2 over 5. And then I get an approximate answer of about 1.756. So x is approximately 1.756.